Hi, welcome to the next section, Introduction to Deep Learning and TensorFlow. In this section, we're going to briefly introduce deep learning and then introduce the basic concepts concerning TensorFlow. Finally, we will take a quick glimpse inside Keras. We build an example of image classification using a convolutional neural network. Now we move on to the first video of this section, Deep Learning at a Glance. In this video, we're going to learn about artificial neural networks and deep architectures. To better understand what deep architecture is, we need to step back and talk about standard artificial neural networks. An artificial neural network, ANN, or simply neural network, is a directed structure that connects an input layer with an output one. Normally, all operations are differentiable, and the overall vectorial function can be easily written as y equals f of x. Here, the x contains all the x from x1 to xn, and the same goes for y. The adjective neural comes from two important elements: the internal structure of a basic computational unit and the interconnections among them. Let's start with the former. In the figure, there's a schematic representation of an artificial neuron. A neuron core is connected with n input channels, each of them characterized by a synaptic weight W. The input is split into its components, and they're multiplied by the corresponding weight and summed. An optional bias can be added to this sum. It works like another weight connected to a unitary input. The resulting sum is filtered by an activation function, f of a, and the output is therefore produced. The main problem with this architecture is that it's intrinsically linear, because the output is always a function of the dot product between the input vector and the weight one. You already know all the limitations that such a system has, therefore it's necessary to step forward and create the first Multilayer Perceptron MLP. In the figure there's a schematic representation of an MLP, with an n-dimensional input, p hidden neurons, and a k-dimensional output. There are 3 layers, even though the number can be larger: the input layer, which receives the input vectors, a hidden layer, and the output one, which is responsible for producing the output. As you can see, every neuron is connected to all the neurons belonging to the next layer, and now we have 2 weight matrices, W equals Wij and H equals Hjk, using the convention that the first index is referred to the previous layer and the second to the following one. Therefore, this is the net input to each hidden neuron and the corresponding output. In the same way, we can compute the network output. As you can see, the network has become highly non-linear, and this feature allows us to model complex scenarios that were impossible to manage with linear methods. But how can we determine the values for all synaptic weights and biases? The most famous algorithm is called backpropagation, and it works in a very simple way. The only important assumption is that both fa (brackets x) must be differentiable. First of all, we need to define an error, loss, function. For many classification tasks, it can be the total squared error. Here we have assumed to have n input samples. Expanding it, we obtain. This function depends on all variables, weights and biases, but we can start from the bottom and consider first only Hjk. For simplicity, I'm not considering the biases as normal weights. Therefore, we can compute the gradients and update the weights. As you can see, the term alpha is back-propagated from the output layer to the hidden one. If there are many hidden layers, this procedure should be repeated recursively until the first layer. The algorithm adopts the gradient descent method, therefore it updates the weights iteratively until convergence. Here, the parameter eta, the Greek letter in the formula, is the learning rate. We will now look at deep architectures. Deep learning architectures are based on a sequence of heterogeneous layers which perform different operations organized in a computational graph. The output of a layer, correctionally reshaped, is fed into the following one until the output, which is normally associated with a loss function, to optimize. The most interesting applications have been possible thanks to this stacking strategy, where the number of variable elements, weights and biases can easily reach over 10 million. Therefore, the ability to capture small details and generalize them exceeds any expectations. Now I'm going to introduce briefly the most important layer types. The first one is a fully connected layer. It is made up of n neurons, and each of them receives all the output values coming from the previous layer. It can be characterized by a weight matrix, a bias vector, and an activation function as shown here. They are normally used as intermediate or output layers, in particular when it's necessary to represent a probability distribution. The next one is convolutional layers. Convolutional layers are normally applied to bidimensional inputs. They are based on the discrete convolution of a small kernel K with a bidimensional input, which can be the output of another convolutional layer. A layer is normally made up of n fixed-size kernels, and their values are considered as weights to learn using a back-propagation algorithm. A convolutional architecture, in most cases, starts with layers with few larger kernels. In this way, the first layers should learn to capture more generic features, while the following ones will be trained to capture smaller and smaller elements. The output of the last convolutional layer is normally flattened and used as input for one or more fully connected layers. In the figure, there's a schematic representation of a convolution over a picture. Each square set of 3 by 3 pixels is convoluted with a Laplacian kernel and transformed into a single value, which corresponds to the sum of upper, lower left and right pixels minus 4 times the central one. To reduce the complexity, when the number of convolutions is very high, one or more pooling layers can be employed. Their task is to transform each group of input points, pixels in an image, into a single value using a predefined strategy. The most common pooling layers are max pooling. Every bidimensional group of open brackets m cross n close brackets pixels is transformed into a single pixel whose value is the greatest in the group. Average pooling. Every bidimensional group of open brackets m cross n close brackets pixels is transformed into a single pixel whose value is the average of the group. In this way, the dimensionality of the original matrix can be reduced with a loss of information. Next is dropout layers. A dropout layer is used to prevent overfitting of the network by randomly setting a fixed number of input elements to 0. This layer is adopted during the training phase, but it's normally deactivated during test, validation, and production phases. Dropout networks can exploit higher learning rates, moving in different directions on the loss surface and excluding all the error surface areas that don't lead to a consistent optimization. Dropout is very useful in very big models, where it increases the overall performance and reduces the risk of freezing some weights and overfitting the model. The last one is recurrent neural networks. A recurrent layer is made up of particular neurons that present recurrent connections so as to bind the state at time t to its previous values. This category of computational cells is particularly useful when it's necessary to capture the temporal dynamics of an input sequence. In many situations, in fact, we expect an output value that must be correlated with the history of the corresponding inputs, But an MLP, as well as the other models that we've discussed, are stateless. Therefore, their output is determined only by the current input. RNNs overcome this problem by providing an internal memory which can capture short-term and long-term dependencies. The most common cells are long short-term memory, LSTM, and gated recurrent unit, GRU, and they can both be trained using a standard back propagation approach. That's all you need to know about deep learning.